Welcome to the next topic. In electronics, we were discussing the semiconductors, and in semiconductors, we were discussing the current due to the charges as a result of electrons and holes. In this particular topic, we will discuss the effect of temperature on semiconductor parameters. So, temperature is basically a very important factor which affect the parameters of any semiconductor. The factors which are affected by the temperature are the intrinsic concentration, the movability, conductivity, and the energy gap. So these factors have been discussed in very detail in the previous lectures, and the energy gap is the difference between conduction band and valence band. We have discussed like what should be the energy gap of the silicon and germanium under intrinsic as well as extrinsic conditions. We have discussed that the electron concentration and the hole concentration formula in the previous lectures in relationship with the number of conduction particles present in the energy gap as well as its relationship with the Fermi level and the other important factors. We have also derived the relationship that the square of the intrinsic concentration is equal to NCNB e to the power minus Eg by kT. So here we can see that the intrinsic concentration is related with the temperature as well as the energy gap. However, it is independent of the Fermi level. So Fermi level is not present in the equation of the intrinsic concentration, and only temperature and the energy gap is going to vary. So we can say that the intrinsic concentration is very sensitive to temperature and is given by this relationship, where we can see that the cube of the temperature variation will be occurring and there will be square of the variation in the intrinsic concentration. So intrinsic concentration is very sensitive to the temperature. The other terms which are associated with the equations are already given here, that is the constant A naught, the temperature in Kelvin, forbidden energy gap Eg naught at 0 Kelvin, and the Boltzmann constant. So the temperature effect on extrinsic semiconductors. So extrinsic means when you have doped the semiconductor with pentavalent or trivalent impurity atoms, then in that case when the temperature increases, the intrinsic concentration increases, which is due to the effective charge density. So the number of charged particles has increased. We know that in n-type semiconductor the majority are the holes, so holes are very more than the electrons, and in p-type semiconductor we know that the electron concentration will increased when the temperature increase. So in n-type and p-type semiconductor we can say that with the increase in the temperature, what happened to the holes and the electrons, which are going to get changed. Next factor we will take the movability. So movability mu is directly proportional to T to the power minus m, where T varies from 100 to 400 Kelvin, and the value of m is a constant which for silicon and germanium are given depending upon the concentration of the charged particles, whether it is electrons or holes. So for silicon you will have 2.5 and 2.7 as electrons and hole concentration, and for germanium you will have 1.66 and 2.33. So when the temperature increases, the mobility decreases. So mobility is inversely proportional to temperature, and the mobility is basically a function of electric field intensity, whose unit is volt per meter. So if we see the mobility below 10 to the power 3 volt per meter, it is a constant, and at a very high range it is inversely proportional, and in the range of 10 to the power 3 to 10 to the power 4 you will have e to the power minus 0.5. So this minus 0.5 comes from here, the minus m. So depending upon what voltage you are applying and what electric field intensity do it have, the mobility will be varying. However, when we talk about the temperature increases, the mobility decreases. Next factor will take the conductivity. We know that conductivity depends upon how many electrons and holes pairs are there and what is the mobility of those charged particles. So when the temperature increases, the electron hole pair increases and mobility decreases, because mobility is inversely proportional to temperature. So number of electron hole pairs will be more than the movability of the particles. So at a temperature T degree Kelvin, we can write an equation of the conductivity as sigma equal to sigma naught 1 plus alpha, and the difference of the temperature T minus T naught. T naught is the initial temperature and alpha is the temperature coefficient. So when the temperature increases for an intrinsic semiconductor, the conductivity increases, and in the extrinsic semiconductor, doped semiconductor, when the temperature increases, the conductivity decreases. So this is inverse prop in intrinsic and extrinsic, as the number of majority carriers is constant. So in extrinsic semiconductor, since it is a doped semiconductor, the majority carriers are constant and only the minority carriers, which are the doped carriers, are changing. So mobility will fall in that. So this mobility relationship we have already discussed for extrinsic semiconductor. Now the final factor is the energy gap. Energy gap is nothing but the difference between the conduction band and the valence band. So the difference between conduction band and valence band, that is dependent on the temperature. So when the temperature increases, the energy gap decreases. This is due to the factor that Eg naught, that is at 0 Kelvin, minus beta into T. So here if you see that this factor will keep on increasing when the temperature will increase. And here the beta is nothing but a constant for silicon and germanium. These values are given as 3.6 into 10 to the power minus 4 and 2.23 into 10 to the power minus 4. The forbidden energy gap Eg naught, that is at 0 Kelvin for silicon and germanium, we know from previous lectures that is 1.21 and 0.785. This is for intrinsic at 0 degree Kelvin. So temperature will increase, then the energy gap will decrease. Now one important topic is what are the different currents which are associated with semiconductor, and these are the drift current and the diffusion current. So the charge flow results in a current, whether it is a semiconductor or a PN junction diode. So next topic we are going to take PN junction diode. There are two different components of the current. One is the drift current and another is the diffusion current, both in the semiconductor as well as in the diode, because diode is made up of semiconductor only. So the drift current, what is drift current? Drift current arises due to the movement of the carriers. So carriers are the charge particles, and you apply electric field. So this electric field will come from the voltage. So when you apply the supply voltage or the electric field, there will be some carriers, and which will result in the current which is known as the drift current. Now the carriers can be holes, which are the positive carriers. So when you apply in the electric field, it will move in the same direction. Whereas when the carriers are electrons, that is the negative carriers, it will move in the opposite direction of the electric field, applied electric field. So the net motion, when we are talking about the charge particle, it is generating a drift current in the same direction as that of the applied field. So this can be visualized with this pictorial representation, that we have applied an electric field in this direction. The electron is moving in the opposite direction and the hole is moving in the same direction as the electric field, and the net drift current is in the same direction of the electric field. So if we give this in terms of equation, drift current density, which is J, unit is ampere per centimeter square, and due to the free electrons and holes, this equation can be given as this. So depending upon the electric field, you will be having the current density for the electrons and the holes. The other factors, we have the charge, which is 1.6 into 10 to the power minus 19 coulomb for an electron, and here you have N and P are basically the number of electrons and number of holes, and mu N and mu P are basically the mobility of electrons and holes, and the unit of electric field is volt per centimeter. Next current what we have is the diffusion current. So in diffusion current, you will have absence of applied voltage. So the voltage will be 0, but the current will flow. So even the voltage is 0, the current is flowing. How? Because there is a concentration gradient exists when the charge particles are there. And these depend upon how many number of electrons and holes are there, which is generated in one region to that of the other region, whether it is a conduction band and the valence band. So when the charge carrier move, it move from higher to lower concentration of the same type, whether it is P or N. And these charge carrier, due to the movement, there will be a current which is resulting in the diffusion current. So due to the potential or the concentration gradient, there will be movement of the charge carrier which is responsible for the diffusion current. However, the applied voltage will be 0. So here we can see the diffusion current due to holes and the diffusion current due to electrons. So holes are represented by positive and electrons are represented by negative, and the movement of holes and the movement and the direction of the current is same, and the current direction is different for the electrons movement. Similarly, diffusion current density in ampere per centimeter square can be given by this relationship for the hole and the electron, which is directly proportional to dp by dx and dn by dx. So these are the concentration gradient. So we can see there is a negative sign appearing in hole, and you will be having a positive sign here for electrons. So hole density decreases with increasing x, hence negative sign. So when the direction is different, so this current, this negative is indicating only the direction of the hole, but the current will be positive. So Jp will be positive in the positive direction, and the dn by dx and dp by dx, these are the concentration gradient, whereas the other term what we have dn by dp is the diffusion coefficient in centimeter square per second. So if we talk about the total current, which is sum of the drift current and the diffusion current what we have, then these two sums will be adding up. So drift current plus diffusion current will be the total current. So in a semiconductor, when you have the drift current due to the electric field and diffusion current when voltage is 0 for the concentration gradient, you will have a current. So Einstein has given a relationship between the mobility and the diffusion coefficient. This is a very particular equation which will be used to determine the charge particles. So Einstein has given this relationship, and this relationship holds that the mobility and diffusion coefficient, so this is the mobility and this is the diffusion coefficient for a particular charge carrier, dp by mu p is equal to dn by mu n, which is for the electrons. So holes is equal to electrons. Hence the charge carrier, when it is greater for the mobility, greater will be the tendency to diffuse. So when the mu value is increasing for the charge carrier, it will have a tendency to diffuse more, so more current will be there. And this equation, Einstein equation, is used to determine dp and dn. So whether it is the diffusion coefficient of holes or diffusion coefficient of electrons, these you can determine experimentally by measuring the mobility. So once you determine the mobility experimentally, you can determine the diffusion coefficient of holes and the electrons. So with this we complete the entire semiconductor chapter, and in the next topic we will take up the p-n junction diode, and this complete the first chapter of the electronics. Thank you for now. See you in the next lecture.